Good evening, everyone. Oh, that was nice. My name is Robin Wheeler-Grange, and I'm the Director of the Office of Community Engagement here at Argonne. And it's my pleasure to welcome you to Argonne's latest installment of the Out Loud Public Lecture Series. Tonight, we will be examining Argonne's past, present, and future through the lens of nuclear energy. Our advancements in this area helped build Argonne's foundation. So thanks again for joining us, and now it's my honor and pleasure to introduce Argonne's Laboratory Director, Paul Kearns. Let me just say a little bit about him. Paul has served as Laboratory Director since 2017, and during that time, he set the laboratory's strategic vision to deliver pivotal discoveries, pioneering leadership, and powerful scientific tools and facilities. We are delighted to have him here tonight to kick off this special Out Loud. And so please, again, welcome Paul Kearns.
Thank you so much. Thank you, Robin. Yes, thank you, Robin. It's really a pleasure to be here this evening, and welcome really to everyone to Argonne National Laboratory, whether you're joining in person here in the auditorium or online. We're really pleased to have you join us this evening. For those who may be new to this series, each Out Loud lecture is an opportunity to hear directly from Argonne researchers about the science and technology that is shaping the world. These events are designed to help make science accessible, spark curiosity, and create conversation between our researchers and the community we serve. Thank you for spending part of your evening with us. You're joining us during an exciting time for the laboratory. This year, we're celebrating Argonne's 80th anniversary, our 2026, yes, thank you. Our 2026 Out Loud lecture series is exploring themes connected to our history, impact, and future. As part of our anniversary celebration, we're also looking forward to welcoming thousands of visitors to our open house next week. For many, it will be an opportunity to see the people, facilities, and capabilities that make discoveries like those discussed tonight possible. It is a sold-out event, but we have some good news for those of you who are interested in attending, and that is if you'll scan the QR code on the screen and select Join the Waitlist, you'll have an opportunity to register, and we certainly hope we're able to accommodate you next weekend for the open house. It looks encouraging right now, so please take the time to do that if you'd like. We'd love to give you a firsthand look at the impact we're making in science and technology right here on the campus. Argonne's anniversary also comes as the United States commemorates its 250th anniversary, making this year a year of reflection for both our laboratory and our nation. Anniversaries remind us that progress is built over time. It also gives us an opportunity to reflect on the advancements we've made. The innovations and technologies we rely on today are the result of generations of people who asked important questions, pursued new ideas, and expanded the boundaries of what was possible. Argonne's history reflects that same idea. Argonne was established, as many of you know, in 1946 as the U.S. Department of Energy National Laboratory, bringing together scientists and engineers to address one of the most defining challenges of the 20th century. Over the following 8 decades, the laboratory evolved alongside the nation's priorities, expanding its capabilities and broadening its impact across science and technology. Argonne is a multidisciplinary laboratory bringing together experts from a wide range of fields to tackle complex challenges and pursue discoveries that matter to our country and the world. Our work lies at the intersection of fundamental science and applied research. Argonne's cutting-edge research spans fields such as artificial intelligence, high-performance computing, material science, quantum information science, energy technologies, and national security. And increasingly, breakthroughs occur when experts from those different disciplines come together in collaboration. Tonight's discussion, Beyond the Reactor, is a fitting topic because nuclear science has been part of Argonne's story from the very beginning. Our founding mission was to develop peaceful uses for nuclear energy. That work required multidisciplinary expertise. The field of nuclear science has always brought together chemists, engineers, physicists, material scientists, mathematicians, and others to solve complex challenges. That remains true today. Modern nuclear technology is being shaped not only by breakthroughs in nuclear science itself, but also by advances in computing, material science, advanced instrumentation, artificial intelligence, and data science. And at the same time, advances in nuclear science continue to create new capabilities and innovations that benefit some of the same areas of science and technology. The exchange of ideas across disciplines is one of Argonne's greatest strengths. It is made possible through collaboration among researchers across scientific fields and through partnerships with universities, industry, and other national laboratories and government agencies. That collaborative approach has helped us to find Argonne for 80 years and remains central to our mission today. As we look ahead, we are confident the next generation of discoveries will come from bringing together expertise, powerful scientific tools, and talented people to solve problems that matter. Now, joining us tonight are several Argonne researchers whose work reflects the themes we have been discussing. With us, we have Stephen DelaCruz, chemical engineer, who will present on our efforts to tap into the power of recycling nuclear fuel through a process that originated here at Argonne more than 7 decades ago. Nora Shaheen, a chemical engineer, will review our cutting-edge sensors that enhance national security and the country's nonproliferation efforts, certainly something that's been in the news of late. And Xuan Zhang, a principal material scientist, will walk us through some of the newest technologies here at Argonne that help us examine materials more comprehensively, enabling discoveries that support the nation's energy goals. As you listen to our researchers, think about questions that you may have because you'll want to engage with us during our question and answer session later in the program. You'll have an opportunity to do just that. First, before we hear from our researchers, we wanted to ensure everyone has the same fundamental knowledge for tonight's discussion. To help set the stage, I'm pleased that we have Mark Williamson, Director of Argonne's Chemical and Fuel Cycle Technologies Division, who will provide some of the basics on nuclear technologies that will help us with the conversation that follows, and also on how Argonne is helping to advance the country's energy goals. With more than 20 years of experience at Argonne, Mark is the ideal expert to guide us through these topics. So please join me in welcoming Mark Williamson. Welcome. Get this out of your way.
Thank you, Paul. Good evening. I'm absolutely delighted to have this opportunity to describe some of our nuclear science and engineering research and development to you this evening. Let me begin with reminding you how those reactors produce all that energy. Oops. So, fission, a neutron floating through the reactor core impinges on the nucleus of a uranium-235 atom. That nucleus becomes unstable. 2 fission fragments, fission products are formed. Some extra neutrons are released to continue the reaction, and a small amount of mass is converted into a large amount of energy. Argonne has a rich history in harnessing that energy through all of its nuclear reactor development activities. The experimental breeder reactor 1 and 2 were liquid metal-cooled reactors. Those reactors demonstrated breeding or producing more fuel than what was being consumed. They also demonstrated fuel recycling and passive or walk-away safety. In between EBR 1 and 2, Argonne studied many variations of water-cooled reactors. Shown on the slide is the experimental boiling water reactor, which really validated the concept of a boiling water reactor and set the design for those reactors in operation today. So all of these test reactors set the standards for today's reactor fleet, and they also set the design goals for advanced reactor systems. EBR1 and EBR2 really set the design goal for fuel efficiency. They demonstrated breeding, or producing more fuel than was being consumed. They demonstrated fuel recycling. They demonstrated management of long-lived fission products to simplify the siting of a repository, and they demonstrated passive safety. That safety design will not allow a 3 Mile Island or a Chernobyl or a Fukushima off-normal event to ever occur with these advanced reactor systems. Now, because the environment in a reactor is quite harsh, scientists and engineers wanted more powerful materials characterization and computing tools to explore these systems. For example, metallurgists wanted to look at materials that had been irradiated in a reactor and study those materials across different length scales. But specifically, they really were interested in the atomic scale and understanding the small changes that occurred when these materials were in a reactor. Reactor physicists were interested in more efficient computing so that they could explore designs, actual designs of reactors rather than simplified geometric designs, and gain particular insights, for example, of coolant flow in the reactor and how that impacts the performance of that system. So the Advanced Photon Source, the Leadership Computing Facility, really fast-tracked nuclear technology development at Argonne. 4 executive orders that were issued last year opened a new era for nuclear energy, accelerating deployment. 2 of those executive orders focused on reforming the approval process, eliminating redundancies while maintaining the U.S. gold standard for safety. One order focused on advanced reactors providing power to national security sites, and the 4th order focused on reinvigorating the nuclear industrial base, accelerating fuel recycling, providing STEM opportunities throughout the country. The overall goal of this is to increase nuclear energy capacity to 400 gigawatts by 2050. That's quadrupling the current amount of power produced by these systems. So the U.S., with 94 reactors, nuclear energy plays a vital role in providing power, electricity to houses, to businesses, and to industry. Illinois is very fortunate. We have 11 reactors. Approximately 60% of our electricity comes from those 11 reactors, and we're very well situated for the future when it comes to electricity production. Thank you to ComEd and Constellation for their constant efforts to keep us with electricity and ahead of the curve. Each of these 94 reactors produces about 20 tons of used fuel per year. So when you add that to the already existing 95,000 tons, it's a tremendous uranium resource for the U.S. And this uranium resource can be used to provide fuel for advanced reactors. So we are in an ideal situation in the U.S. with the recycling for many years of reactor operation with the fuel supply that we have. So with that brief introduction to nuclear energy, let me now introduce Stephen DelaCruz, and Stephen will tell you more about nuclear fuel recycling.
So let's talk about nuclear fuel. What does it look like and where does it go during its lifetime? Traditional fuel is solid and contained in nuclear fuel rods. Inside each rod are hundreds of Tootsie Roll-sized pellets made of uranium oxide stacked several feet high. These rods are bundled together and inserted into the nuclear reactor. After 3 to 4 years of operation and fissioning, these rods are taken out of the reactor and kept on site in deep water pools to cool and eventually dry cask storage. And while this is currently manageable, there are a few issues that will need to be addressed. First, the used fuel needs to be stored for 300,000 years before reaching naturally occurring levels of radiation. Second, there is no disposal pathway for the long-term storage of high-level nuclear waste. It is stuck on reactor sites in interim storage indefinitely. In fact, the United States pays millions of dollars to reactor companies every year to keep their waste on site. And lastly, for us to reach our 2050 nuclear energy goals, more uranium will be needed, more uranium will be used, and more waste will have to be managed. Now, these issues may sound worrisome, but here's the key. 97% of what comes out of current nuclear reactors is still mostly uranium and a little bit of other fuel elements like plutonium. The remaining 3% are elements that make nuclear fission inefficient, but they could have use for other industries, like medically relevant isotopes or critical materials used to make batteries or magnets. 97% is a considerable amount of fuel that could be recycled. But how do we actually go about recovering this usable fuel from the waste? Our proposed method is power processing to take the waste and turn it back into fuel. Power processing was pioneered at Argonne in the 1950s, and since then, we've been developing and advancing the state of the technology. It's called pyroprocessing because it uses hot molten salt and electricity to treat the used fuel. Imagine something similar to table salt that's been heated up until it melts into a liquid as our medium for pyroprocessing. So how does power processing fit into the nuclear fuel cycle? Well, first, it takes the waste that comes out of the nuclear reactor, separates out the useful fuel elements, and uses that to make new metal fuel for next generation advanced nuclear reactors. Now, this is ideal because A, these advanced reactors do not have a reliable pathway to obtain the fuel that they need. And B, with pyroprocessing, these advanced reactors could theoretically extract 100% of the energy content from the mined uranium. Second, the treated waste that comes out of power processing is much smaller in volume compared to the original waste. This means we need much less space for long-term storage. And finally, through power processing, we remove the long-lived radioactive elements from the used fuel. This significantly reduces the time necessary for long-term storage, going from 300,000 years to only 300 years. So what does power processing treatment look like? Power processing is made up of several complex integrated operations, but we can summarize it into 3 major steps. Step 1, preparing the used fuel for processing. This involves chopping up the used fuel rods, exposing the fuel meat, immersing it into the molten salt, and converting it from the oxide to the metal so that we can better perform electrochemical separation. Step 2, we take the output of step 1 and use electricity to dissolve the fuel into the molten salt. We can then separate out the uranium and the plutonium from the fuel rod cladding and the non-fuel elements. The purified metal can then be melted into metal bars and used to make new fuel for advanced reactors. Step 3, we take the molten salt that has now accumulated the non-fuel elements and we can separate out those elements into a form suitable for long-term waste storage. The now purified molten salt can then be recycled back into steps 1 and 2. Currently, we are working with industry leaders to test, improve, and scale up our technology to increase their commercial readiness. As a preview for the next presentation, we are incorporating a variety of sensors to monitor our systems in real time and improve their efficiency. We are also adapting our technology to reach broader application spaces here at the laboratory, like critical materials recovery, to make new batteries. Ultimately, we believe power processing will help bolster and expand nuclear energy by closing the nuclear fuel cycle, reducing waste volume and lifetime, and by supplying new fuel for the future. And now I hand it off to my colleague, Nora Shaheen, to talk about sensors.
So thank you, Stephen. To commercialize not only power processing facilities, but also advanced nuclear reactors, we need to be able to monitor the operational health of these systems and track the nuclear material inside of them. So that's where my group and I come in. We are focusing on developing sensors and simulations to do just that. The sensors that we're developing not only help with process monitoring and nuclear material accountancy, but it also provides near real-time positive feedback to operators and designers like Stephen as to how well their systems are operating, such that if an issue arises, we can provide feedback for him to, or for designers and operators to address issues as promptly as possible. So some of you may be asking, well, why do these sensors matter? We can just close up the system and call it a day. Well, we really wish it were that simple. However, in order for us to meet regulatory requirements set forth by the U.S. Nuclear Regulatory Commission and the International Atomic Energy Agency, we need to be able to answer questions relating to quantities and locations of these nuclear materials. Ultimately, these are where our sensors that we're developing at Argonne come in. They're able to do so reliably with high precision and also in a timely manner. Typically, we get results on the order of seconds or minutes. Ultimately, our sensors make it easier for us to monitor these systems and inherently increase the system safety. Not only do they meet these objectives, but they also increase product purity, increase process efficiency, and help us meet non-proliferation objectives, which aims at improving, or rather targeting, peaceful uses of nuclear energy. So in talking about the types of sensors that are currently under development at Argonne, a single slide is simply not enough to discuss both the wealth and breadth of technological development at Argonne. But if I could broadly group them into two categories, I could touch on solid phase sensors and liquid phase sensors. So as the name implies, solid phase sensors track solid phase particles that form due to any number of reasons, including air leaks, salt impurities, solid phase formation just due to fission reactions, and also just any type of reaction that would just form a solid particulate. Our liquid phase sensors help us identify and quantify dissolved materials in both molten salts and liquid metals. They operate by identifying unique fingerprints associated with components of interest. The intensity of that fingerprint tells us exactly how much of that material is in our system. So at Argonne, we're not only interested in developing these technologies, but also testing them and deploying them in industrially relevant and practical systems. So the laboratory capabilities are aimed at just that. Not only do we have engineering scale pyro processing facilities on site, but we also have flowing salt and liquid metal systems. These systems are operating at a variety of flow rates and sizes, as low as a few pounds of material, all the way up to several hundred or even several thousand pounds of material. And Argonne is unique in that we are one of the only national labs in the country that has these capabilities, but also has the capabilities of handling these nuclear materials in these types of facilities. So we're able to test our sensors under practical environments and couple that data, the experimental data, with our computer models and digital twins that are developed by others on our team at Argonne. And from that, we're able to get a holistic picture as to how well these sensors are performing and if there are potential pathways for improvement. Ultimately, this is just part of a broader impact of R&D capabilities at the laboratory. Our R&D capabilities span any number of categories, including process monitoring, including pumped molten salt flow loops, the metal facility on site, multi-scale modeling and simulation tools, as well as chemistry control, where we have capabilities for salt purification and corrosion control. We also have a number of materials testing laboratories on site, including the advanced photon source, which you heard Mark talk about a little bit. And also what you'll hear from the next speaker is the activated materials laboratory. Ultimately, these capabilities allow for us to extend our sensors into application areas beyond nuclear, into critical materials, recovery and production, energy storage through molten salt batteries and concentrating solar power, as well as manufacturing and process industries, including those on the national and international scale. So with that, I'd like to thank you all for attending today's talk, and I'll pass it over to my colleague Xuan, who will be talking about our laboratory capabilities in greater detail.
Good evening. So now you have heard quite a lot about reactor fuel and fuel technologies. Let's switch gear to talk about the materials that we actually use to build the reactors. Those materials are just as critical. However, they live in an environment that can only be described as hostile. There's irradiation from neutron bombardment from the fission process. There's corrosion from constant interacting with the reactor coolants, and there's also mechanical stress from components interacting with each other. On top of all of this is a high temperature. So over time, the material will suffer and their performance will degrade, and eventually they may become even damaged. So to keep the current fleet of nuclear reactors operating safely and to deploy the next generation of nuclear reactors, we have to dive deep into the very mechanisms that lead to these materials changes. At Argonne National Laboratory, we have built a world-class toolkit to help tackle these materials mysteries. Two of the most incredible tools are the Advanced Photon Source, APS, and the Argonne Leadership Computing Facility, ALCF. The APS is a giant ultra-bright X-ray light source. Think of it as a microscope of incredible X-ray power. While a standard X-ray machine in a doctor's office may show you a broken bone, these X-rays produced by the APS can reveal the exact mechanisms of how a material begins to fail. Accompanying the APS is the ALCF, which houses some of the world's fastest supercomputers. We utilize those supercomputers to simulate the evolution of nuclear materials and reactor components over long periods of time, which allows us to stay one step ahead of potential issues. Despite having these great tools, researching nuclear materials is presented with a unique challenge: radioactivity. Common materials like stainless steels become radioactive after serving in nuclear reactors due to the neutron bombardment. For a long period of time, using these advanced instruments like the APS to handle highly radioactive samples for study is considered prohibitive due to the complexity in handling radioactivity. To bridge this gap, We opened the Activated Materials Laboratory in July 2025 after nearly 2 decades of dedicated hard work, which laid the foundation. I personally contributed and eventually led the whole process. So the AML is a user facility, meaning it is open to a broad range of research community from universities to national labs and to industry. Its primary mission is to safely prepare radioactive samples so that they can be studied at the APS beamlines. We also utilize the ALCF to conduct analysis on the data that's coming out of these APS experiments. The AML really transformed how we work. Technology that used to be out of reach for radioactive material study are now become readily available thanks to our specialized expertise and safety protocols. One of the most exciting aspects to use the APS X-rays to study radioactive nuclear material is the ability to perform non-destructive probing. In the past, to see through a nuclear sample, you often have to cut it open, which not only destroyed the very thing you were trying to study, but also generated a lot of radioactive waste. Now, thanks to the high energy of the APS X-rays, we can peer through thick bulk volume of material like millimeter or even centimeter thick steels without doing much modification to the samples. In addition, we can use 3D technologies like X-ray computed tomography in many ways similar to medical CT scans to generate 3D rendering of the samples, which can allow us to see interesting features down to micrometer levels. But we do not just take still photos. We also conduct real-time dynamic studies, placing materials under heat or stress, and watch how this material evolve as the process unfolds. Due to the high intensity of the APS X-ray light, we can take pictures of the samples at super high speed, allowing us to capture the exact moments that material begins to change. To better explain the impact of our work, let me show you a real-world example. Recently, we teamed up with a group of researchers from University of Illinois to study a real reactor component, a baffle former bolt. These bolts are critical to the integrity of the reactor structure, but they are prone to a phenomenon known as irradiation-assisted stress corrosion cracking, which usually happens around the shoulder area of the bolt, where stresses are usually the highest. So in this particular case, the bolt was discovered during routine inspection of a reactor in the New York state and was hence retrieved and replaced. The researchers cut samples out of these bolts and shipped them to the AML. The AML helped them to prepare the samples and transported them to APS beamline for X-ray study. We performed 3D X-ray mapping on these materials, which revealed the path that the crack took inside the metallic body. We were also able to map the teeny tiny crystals known as grains that made up the material. By understanding what characteristics these grains have that actually promoted the growth and propagation of the cracks, we are able to engineer better, stronger alloys for future reactors. This research is more than just a scientific success. It is actually a historic moment. It marked the first time an APS X-ray beamline end station was temporarily transformed into a radiation area due to the presence of highly activated samples. This achievement was officially recognized by the Department of Energy as a nuclear milestone. The work we do in the AML, in collaboration with the APS and the ALCF, is shaping the future of nuclear energy. By providing the broad research community with access to these tools, we are ready to help with the safe operation of the current fleet of reactors so that they keep serving as the backbone of our carbon-free energy grid, as well as help to pave the way for the deployment of advanced reactors. Thank you.
Well, thank you very much, Xuan. Please have a seat. I'll ask Mark and Stephen, as well as Nora, to join us on stage. So that'd be wonderful. Thank you. As we move, transition really into our Q&A session, but please another round of applause for our speakers. Now we have an opportunity really to hear from our audience. We're pleased to have you join in the conversation. So I'm going to ask those that are here present in the room to join us, if you have a question, to join us at the back of the room here and line up behind the microphone, certainly. That'd be wonderful. If you have a question and you're joining us virtually, please type your question into the chat. We'll take our first question from right here in the room. So please, I'll help moderate the conversation. I may lead in with a response to a question or two along the way as well. So can't quite see very well here, given that really bright light back there, but I think someone's in the line here, so please.
Yeah. In the early 70s, they built the Morris operation. And then by 1974, they changed over from trying to reprocess or recycle nuclear energy, and they store it. I'd like to know what transpired between 74 and now, where we actually can do the recycling.
Yeah, good question. Mark, that sounds like one right in your sweet spot in terms of expertise, so please.
Yeah, certainly. Thank you for the question. You remember in 1977, President Carter paused recycling in the United States, and that stayed into effect until the 1980s when President Reagan rescinded that. By that time, recycling and had dwindled. Recycling research and development had dwindled in the United States, and it took some time to restart that activity. In the late 80s, Argonne started the Integral Fast Reactor program, which was really focused on those advanced reactors with continuous recycling of the fuel to really achieve recover 100% of the energy content from uranium. So it was that pause that the United States took from 77, let me say, until about 1988.
Do you guys actually do for real recycling here right now?
So we do research with simulated materials. We do not have irradiated materials that we use in our recycling processes.
Thank you.
Yeah.
Good evening, and thank you for the presentation. I come from a non-science background. I come as a former community resider in the area, lived by Argonne for 40, 50 years, and this place has always been like a mystery. My concern is the storage and the handling of this dangerous materials. Do we have to worry about getting into our water tables? Do we have to worry about like the smoke that comes out of the chimneys around here? So how do you contain and protect us from the dangerous materials?
Yeah, there's quite an effort really underway here at the laboratory to make sure that we're taking care of legacy research materials that we have on site. They're safely stored in really robust hot cells or storage facilities here at the laboratory where they're prepared for shipment, and many of them are shipped off-site to other places for disposal. So that's one key aspect of it. There are no ongoing operations really that generate radioactive material that you need to be concerned about. We do have minuscule quantities of radioactive materials we use in our research on a daily basis. All of our activities in that regard really follow the latest requirements in terms of procedures and containment and control, and either from the Department of Energy or other regulatory agencies here in the state of Illinois. We'd be happy to really take the opportunity to have a more detailed conversation with you. But I think, Mark, do you want to add something here as well, or maybe one of the other folks in terms of really how we handle our radioactive materials here on site? Argonne's been very responsible over the time that I've been the director, which has been quite some time, and here at the laboratory at this point, but please.
I mean, I think that the nuclear industry as a whole is very careful about, maintaining levels of safety and regulation. Like when I come to work, I feel very protected when I work with the radioactive materials that we do have, because there's so many barriers to protect me and the environment from the materials we handle. Like Mark mentioned, we use safer versions of the radioactive material for our research, like depleted uranium rather than more irradiated stuff. And we have entire groups on campus who constantly check to make sure that all of our barriers in that material are up to date, tested, so that not only we are protected, but the environment around us. So I feel very comfortable coming to work every day and not having to worry about possibly, hurting myself.
And you wear badges to regulate your exposure?
We wear like dosimeters to monitor our dosages. Mine come back 0 every time. We have instrumentation to make sure that whenever we leave the laboratory, we're always surveyed clean. We're not bringing any materials out of it. And so there are a lot of people and technology incorporated at the laboratory to really protect us.
Thank you.
Yeah, of
Thank
course.
you.
Good evening. My name is Jonathan. I'm a freshman in high school, and I just want to say thank you for this presentation. And my question is, what are some things I could do, like in or out of school, to help me prepare for a future career in nuclear engineering?
Fantastic.
I could maybe step
Please.
in quickly.
Please, Nora.
Yeah, I think just getting involved with various STEM clubs in high school, and as you transition into college, just getting involved with as much, I would say, experience in whether it be through clubs or just different types of science-based classes. But I think it's also important to remember that science is also creative, and so tapping into the creative side of your brain in terms of getting more experiences and versatile experiences that way. And I think you'll find yourself kind of making your way into that space with time.
I can also say something. But you can also remember that a person's career change, right? So for example, myself, I started, my undergrad was on physics and then moved to material science and then sort of get into this nuclear field. But I think the most important thing is to stay curious, have really good overall scientific study and background, and also, if you can, get in contact with people of the field that you are interested in and keep the conversation going. So those are all great ways and eventually will lead to where you would like to be.
Thank you.
Yeah,
And
thank
intern at Argonne.
you. Thank you for the question. Please, I don't know if we have any questions online, or we do, okay.
Are you able to hear me? Okay, there it is. We have some great questions online, actually many, so I'm going to try to condense them. So you folks online, apologies for condensation. One question we have around what happens in other national contexts around using fuel efficiently? Do you have any examples that we're trying to integrate into our own processes here? And then there's another question around ways to mitigate refueling shutdown periods in U.S. reactors. And for example, the Canadian reactors employ continuous fueling arrangement and avoid the requirement that they shut down for fueling. So could you maybe speak to other national contexts and how Argonne is thinking about those approaches?
Would you like to jump in? Mark, please.
Yeah, thank you, Paul. Great questions. We have examined other technologies that are in use in France, the UK, Japan, elsewhere, and really looking at the technologies from a resource utilization perspective, from a waste management or waste stewardship perspective, and economic and U.S. Economic perspective. We've really honed in on the pyroprocessing technology, as well as several aqueous technologies that are a bit less mature, but we're studying those as well. The Canadians, that particular reactor type uses a tremendous amount of uranium, and it produces a significant amount of waste that needs to be dealt with. And the reactors that we're looking at in the US with the continuous recycling would allow you to basically recover 100% of the energy content from the mined uranium. So it's a really efficient way to produce energy for the grid.
Yeah, thank you. Mark, is this also an opportunity to talk about some of the work we're doing with industry?
Yeah, so we are working with several industrial partners. We have funding through the Department of Energy Advanced Research Projects Agency, Energy. We also have some directly funded work from industry, maturing our pyroprocessing technology, looking at industrialization of that technology, bridging the gap between applied science to commercialization or to deployment. We love to work in that in-between area of industrialization and work with industry to help them drive to deployment.
Yeah, thank you. Thank you. Please.
Sorry. Good evening. When you spoke on the pyroprocessing, which is like the recycling, you mentioned that there is still like a certain amount of material that's left over while it's like significantly reduced. Is that still enough to be something that we should be concerned about? And if so, do you see like a future where we also recycle those materials as well?
That's a great question. Oh, that's a great question. So right now, right, we have a once through nuclear fuel cycle, meaning that that material as well as the unused fuel are still on the path for disposal. And so power processing, we're trying to reduce that volume and that lifetime for storage. When it comes to material that we don't recover, that's not the non-fuel elements, I think there's a lot of work and research that could be invested to how do we go about recovering that material and actually making some use out of it for, say, radioisotopes or critical materials for energy devices. That said, though, if we don't touch that, we have developed in our division waste forms that are suitable for that long-term disposal. We're trying to understand and improve how stable they are for long-term storage. And so we're trying to develop the tools and solutions to make sure that that leftover waste is stable across the time period of storage. So hopefully that answers your question.
Yeah, thank you.
So Paul, may I?
Please.
Yeah, so just to follow up, Stephen mentioned earlier that some of those materials could be reused. We actually have a project with an industrial partner where we're recovering some of those elements that can be used in electric generators. And those electric generators then provide power to spacecraft. So there are materials that can be reused. We're looking at those, but to Stephen's point, we have a very robust program in developing waste forms that are durable and long-lasting and will meet that 300-year or more requirement for storage.
Yeah, excellent question.
All right, we're going to take one more from the chat. Can you provide some examples of commercializing fuel recycling technologies here in the US and elsewhere? And then what are the economies of recycling fuel versus mining fuel?
So like Mark mentioned, we're working with various industry leaders to develop our processes and integrate them with their plans as well. And so there are ongoing commercial developments on that end to really integrate recycling into the nuclear fuel cycle. In terms of other countries, I believe other countries also do some form of recycling, and so it just kind of makes sense for us to also integrate that here at home.
And I would add to what Stephen said. The U.S. has the goal of quadrupling our nuclear energy to 400 gigawatts electric by 2050. That will require quite a few more reactors. It will require quite a large amount of uranium. And the uranium that we currently have in the US, the 95,000 tons of used fuel, could be used there. The US also has other uranium resources already available that wouldn't require additional mining. So to take advantage of that valuable resource, the recycling is a very cost-effective way to move forward.
Yeah, thank you, Mark. I know we've got people lined up for questions. I appreciate everybody's patience, so please.
Good evening. Thank you very much for your talk. My name is Andrew. I have a question. Would your research in advanced reactors eliminate the need for repository sites like Yucca Mountain, where waste would be stored for tens of thousands of years?
Our recycling process does not eliminate the need for a geological repository, but it greatly simplifies the requirements for that repository. That 3% of material that Stephen mentioned, the majority of that would need to be disposed in a geologic repository, but instead of spending time, instead of requiring over 300,000 years to decay back to the level of natural uranium, it only requires 300 years. So we do still need a repository, but it's a very simplified design compared to Yucca Mountain.
Yeah, thank you for the question. Please. You're up, I think. We're being encouraged to look at this as the lightning round that keep our responses short. Please.
Good evening. Thank you for inviting us to the crown jewel of the national labs. The question I have is, my perception of the nuclear industry in the United States is that it's very complex. The nuclear reactors were not modularized in their designs. We have many different types of designs which drove up costs and all that sort of stuff. I believe the French standardized a nuclear reactor design in the 70s, and I think they get 55% or 60% of their energy from nuclear energy in France. What's happening with small modular reactors? So instead of scaling up, you're scaling down, and then you're creating like arrays of these small nuclear reactors that are much more simplified. So what work are you guys doing in that area?
So the lab is doing quite a bit of work with industry partners in those areas, and I think what you just described is exactly a goal of many of the industry folks. Modularization to decrease cost, factory manufacturing so that they can take the components to the site and assemble them. So that is the goal of quite a few of the industry, reactor industry folks. And the size of the reactor really depends more on the end use. You can have quite large modular reactors that can be factory fabricated, a gigawatt of thermal power, a large system. Also, you can have microreactors, which goes even smaller than SMRs. So industry is finding the niches for all of these reactors, and as you point out, the goal is modularization to stabilize cost and provide the necessary power.
Yeah, thank you very much. Unfortunately, I've been
told that we're out of time for Q&A. It feels like we just got started. It's a hot topic. It's a complicated topic as well, and so I appreciate everybody's patience. We have asked our panelists, the researchers, if they would be willing to take field questions one-on-one after the formal closure of the event, and they've all said yes, they'd be happy to stay around and answer questions as part of a more informal dialogue. But thank you so much, really, for the active engagement. As I said, it's a complicated and critically important topic, and I appreciate the questions as well about Argonne stewardship, really, and how we work with radioactive materials. Certainly, top of mind for me every day is really being a really positive member of the community, and I often talk about our people being the most important aspect of the laboratory. They really enable the work we do, and so keeping them safe is of utmost importance as well. We do have a very active community leaders roundtable that follows our activities on a regular basis as well, and so we make sure they're aware of what's going on site, and appreciate their engagement, their support, and the difficult questions they ask from time to time of the laboratory. So I wanted to kind of finish up on that question a bit. So before we conclude, we would like to direct your attention to the Q&R code that's on the screen, which will take you to a quick survey with a handful of questions about your experience at tonight's events. Your feedback really will help us improve planning future planning this series in the future. So thank you so much for your input. Please take a few minutes and provide that for us. It's quite helpful. And if you're interested in revisiting tonight's lecture, or if you would like to share with someone who couldn't join us, you'll be able to find this, as was mentioned earlier, on Argonne's YouTube channel in about a week. You can also visit our Argonne OutLoud archive page on our website for the link. So before we let you go tonight, we have a few special surprises for you tonight, and I need to turn it over to Courtney at this point in time. So please hold your seats. Courtney, please.
Thank you so much, Paul. What a treat it is to have our laboratory director, Paul Kearns, moderating this out loud. Can you please give him a round of applause? This man is so busy, especially today. I don't even want to tell you what his schedule looked like today. But I tell you, if this is the first Out Loud you've ever attended, can you please raise your hand? I'm just curious. Perfect. Guess what? You guys are so lucky you came to the right one, because we have a lot of surprises and treats for you today. So as you just heard, this is our 80th anniversary, and we're just a few days away. July 1st is going to be here before you know it. So while you are here with us, we want to celebrate our 80th anniversary with you. So you can see this lovely cake here. Isn't that lovely? We want to ask our laboratory our laboratory leaders to come up and join Paul, because we're going to have a very special cake cutting ceremony. So our lab leaders, if you can come on up and join Paul. Isn't that cool? You see our little delta on there? All right, so guess what, guys? We're turning this into a party, okay? So we have the cake, but before we cut it, what are you supposed to do before you cut the cake? Okay, what are we supposed to sing? Happy birthday, exactly right. So guess what? We're gonna sing Happy Birthday Argonne. We're gonna change the lyrics just a little bit. We're gonna project them up here just for you, and guess what? I'm gonna lead the singing, and I apologize in advance because I cannot sing. So I really want you to sing very loudly so that you can drown me out. So on the count of 3, we're gonna go all together, okay? 1, 2, 3. Happy birthday, Argonne. Happy birthday, dear Argonne. Happy birthday to you. All right. That was fantastic, guys. You guys definitely supported me. I didn't tell any lies when I told you all I could not sing. Now we're going to turn over this cake cutting ceremony to our wonderful laboratory director, Paul Kearns. Paul?
Well, happy birthday, Argonne, and America as well. So thank you all for celebrating with us tonight. Certainly 80 years of discovery here at the laboratory, 250 years of progress here in the United States, and a much brighter future ahead. So with that, let me cut the cake, huh? Yeah. There we go. All right. Yay.
Fantastic. Thank you so much, Paul.
Get out of the way.
Thank you to our laboratory leaders, our leadership up here, and as well as our speakers tonight. This was a very special topic. It's been a pleasure working with you guys. I forgot to introduce myself. I'm just up here talking to you. My name is Courtney Gooseman. So I do communications. I lead communications for the Office of Community Engagement here at Argonne. So one of my biggest responsibilities is managing this Out Loud lecture series. So some of you I probably emailed. You were talking to me. So thank you so much for being here tonight. We really appreciate having you. And we have some more surprises for you. Do you guys want some cake? Okay, good. All right, what we're gonna do is we have some treats for you, free, and free. So we have some giveaway bags for you, and I'll just give you a special note, they're fragile. So, and then we have some cupcakes for you, courtesy of Sylvia's Bakery, which is down the street in Darien. So everything is prepackaged for you to go. So what we'll do is, once we dismiss here, we'll take the 2 exits. You can use either exit, and we have staff in place that'll help make your way across the hall to our party room. That's where we're having the after party, folks.